Okay. All right. So the past few weeks we've been looking at limits and how to find the limit going to a point or to infinity. The very first thing we looked at when we first started looking at it was a tangent line and slope. And actually the first question in your test was actually to find the slope of a tangent line and then find the actual equation for that tangent line. So if you think about what the equation for slope is, it's y2 minus y1 over x2 minus x1, right? So it's those 2 points. In essence, that's what we have here. You have f of x, which is your y. You have f of a, which is the equation when you plug in a number, over the x minus the a, which is your x values of x1 and x2. So if we take that as a limit as x goes to a, the bottom is going to go to 0, which means we're looking at the slope as the 2 points get infinitely close together. You're going to see this type of equation, or this equation, written like 4 different ways today. So don't stress so much about writing everything down. Just the function's fine. All right, let's actually use this to find the slope of a tangent line. Everybody got the equation written down? You don't really need everything else, just the equation. Okay. All right, so that's the function. So we're looking for the equation of a tangent line of y equals x squared at 0.11. So what's f of x? Is x squared. Because remember, y and f of x are basically the same thing. They're interchangeable. So what's a? That's the one. That's the one in the point. So that's a. So what's f of a? Also 1. That's f of a. Okay. So I have the limit as x goes to 1 of x squared minus 1 over x minus 1. So how do I solve it? All right, so let's factor the top. What's that going to give me? What's factoring the top going to give me? Okay. And then I can cross that and that off, right? So then I have the limit as x goes to 1 of just x plus 1, which is 2. So that's m. So then if I want to find my equation, we can use the point slope equation. So it's y minus 1 equals 2, x minus 1. So y equals 2x. 2 plus 1. Oh, no, sorry, minus 1. And then that would be my equation of y. So we can start to see how using the slope equation saves me a lot of time and effort of going through and using out the like points and stuff that we did at the very beginning. This is the equation we typically will see used. The only difference it does is instead of putting x minus a on the bottom, so what it's changing is x minus a is h. So then x is the same as saying a plus h. So it's just replacing that. So instead of having a function down the bottom, we just have a single letter down the bottom. So this way it's a little bit easier when we're trying to factor out. We're going to be factoring out the h, which you've done a couple times. We did a couple problems like that in the last section. So let's use it to do this. I'm just going to write the problem again anyway, so you guys will still see. Sorry, h goes to 0. All right, so f of x is 3 over x. My point, so that's a, and that's f of a. So what we really need is f of a, yes. They just want, so this way you don't have that function down the bottom. It's just another way to write it so there's only one letter. It was just a way to rewrite that problem. So we're going to be factoring out a letter, which is easier to do a lot of times than trying to factor and break down functions. Yeah, it's just an easier way to write it. This one works well when it's like a simple problem like this, because it's easy to factor. When we're looking at more complicated problems like this one, it becomes really hard to see what you're factoring out when we have a lot of extra terms. So by just making it an h, it saves us a little bit of that work. All right, so what is f of a plus h? Well, a is what? 3, right? So what's f of 3 plus h? Yeah. Remember, all that does is just replace the x. So I have 3 over 3 plus h minus 1 over h. All right, so let's just look at that part first. Okay, let's clean that up a little bit and see if I can somehow get the h out. So how would I put those two together to kind of make my life a little bit easier? Yeah, and the denominator in this one's just 1, right? So I'm going to have 3 over 3 plus h minus 3 plus h over 3 plus h. So 3 minus 3 is 0. So I have minus h over 3 plus h on the top. Right? That makes sense? So now that whole thing was over h, right? If I took that, put it down the bottom. So how do I do division of fractions? Keep flip change. So this is negative h over 3 plus h times 1 over h. So now we can do the limit as h goes to 0. Negative 1 over 3 plus h which goes to -1. Okay. So again, we're just using this function, this limit function, to come up with my slopes, which we then can use for my tangent lines. When you're driving in your car, how do you state your speed? How fast are you going? Give me a speed. 65 what? Miles per hour. Because the miles per hour is the key to this whole concept. What's slope? It's something over something, right? Speed is miles over hours, or distance over time. Okay, that's your rate. That is a slope. Okay, so velocity or speed is just slope of wherever you are divided by time. Okay. So if we wanted to find out exactly how fast you're going at any given spot, or what's known as instantaneous velocity, I want to know how fast you're going when the time is basically 0. That's instantaneous velocity. So velocity is just exactly what we just did. It is just the slope. So it's the same equation. Okay. So as long as time is going to 0, that's going to give me my instantaneous velocity. The whole concept of calculus is rocket science. Well, this is why. One of the most important things when you're setting up a rocket is you need to know the forces on that rocket at any given moment. Okay? You need to know exactly how fast it's going at any given moment. That's instantaneous velocity. You need to know its instantaneous acceleration. You need to know its instantaneous, the forces that are on it, the gravitational forces, those type of things. All instantaneous, because you need to know at every given moment. We can't average it out over time, because when we're averaging it, we might miss something. All right. So these concepts allow us to start looking at what's happening at any given moment. It's literally the same equation, just with a v put in front of it. I'm never going to ask you what the definitions are. All right. Suppose a ball is dropped from the upper deck of the CN tower, 450 meters above the ground. What is the velocity of the ball after 5 seconds? All right, who's taking physics? What's the formula for what is the equation of motion? That's what I was asking. What is the distance in meters after as something is falling? Do you remember? I've never told you in this class, so I know it's not going to be in any of these notes. All right. Yes. So your S, which is known as your position, it's not speed, it's position, is 4.9 t squared. What's the equation what's the 4.9 is not number you normally see. What's the number you normally would see? Why? 9.8 is gravity. Okay. So let's keep that in mind for a second. That's typically G, or not Q, G, right? All right. So we're going to take this equation and let's find the velocity. So that means the limit as h goes to 0 of f of a plus h minus f of a over h. Because that's velocity at a. So that means my limit as h goes to 0 of 4.9 times a plus h squared minus 4.9 a squared over h. Correct? Okay. FOIL out a plus h squared. And it's not a squared plus h squared. Minus 4.9 a squared. We're going to ignore the, we're just going to look at this part for a second. So then I got 4.9 a squared plus 9.8 AH plus 4.9 h squared minus 4.9 a squared, right? So I got 9.8 AH plus 4.9 h squared. Can I pull anything out of that? I can pull out the 4.9. Well, what's the more important thing to pull out? The h. Because I want to be able to somehow, remember, I saw that h down the bottom, right? I have to get rid of that h down the bottom. So actually, let's just pull out the h. So by pulling that out, I now have of h 9.8 a plus 4.9 h over h. Those two h's will cancel out. And as that h goes to 0, what does this go to? Because that's going to go to 0, right? So all that's going to be left is 9.8 a. What does 9.8 represent? What's the unit on 9.8? Meters per second. So it's a slope. It's a velocity. So when we were looking at my original problem up here, that's the position. That's the velocity. So that's where your 9.8 came from. Okay. So now, how fast is it going after 5 seconds? So it'd be 9.8 times 5, right? Which is what? 49? Exactly. Oh, it is. Yeah, 49 meters per second. So when a equals 5, your velocity of 5 is 49 meters per second. How fast is how fast is the ball traveling when it hits the ground? What's the one thing I need to know before I can do this problem? How long is it in the air for? So how would I figure that out? Huh? The height's what? 450. So S was how far we were going, right? So we'll set that to 450, and we can solve this for t to figure out how long it's going to be in the air. So if I do 450 equals 4.9 t squared, so I get 4.9 t squared. How'd I get rid of the square? Not square both sides. Square root both sides. So 9.58 equals t. Approximately. So then we do 9.8 times 9.58. And we get 91.8 meters per second. Yeah. S isn't speed. S stands for, the S equation is your position of the actual object. So it's its position in space, basically. There's lots of letters we use that, like, because they're not all made in English. is the big thing, yeah. So it's not. So that's why when we look at it, it's like, hey, wait, S is speed. No, S isn't speed. Velocity is speed. So V would actually be the speed in that respect. So. All right. So we spent a whole bunch of time finding slope. Why? Well, because that's what a derivative is. So here's the entire rest of your Calc 1 experience for all intents and purposes. So the derivative of a function is its slope. The key thing that we're going to be looking at when we're moving on, and we're going to start doing things is, so far everything we found until the very last one was at an exact point. We did the limit to a point. And the last one, we didn't do the limit to a point, we did the limit to a, because we wanted a function that we could then use to plug values into. That's what the vast majority of your derivatives are going to be. We're going to take a function and we're going to find its derivative, because then we can then use that derivative to do other things. All right. So if I have a position function for an object and I find the derivative of that, I can then find the velocity at any specific point. Or I can then take the derivative of that and find the acceleration at any given point. So we can start doing more and more things to it. After today, you're not going to use this equation. We're going to actually use rules to find the derivatives. But it is nice to be able to understand where it's actually coming from and what it actually means. All those symbols down below it are all different ways people represent derivatives. Okay. The ones we're going to see most often are those. All right, you're going to see f prime of x. That little symbol is known as prime, or y prime, or dy dx. Okay, those are the three ways you're going to typically see it. The f prime of x and y prime are Newtonian calculus. The dy dx is Leibniz. Okay, so remember, there's two people that created calculus at almost the exact same time, Newton and Leibniz. And they both did it the same way. The rules came out to be the same. Their notations were slightly different. Yes. It's called prime. Yeah. That little apostrophe is when I say f prime of x, that's what that apostrophe is, or y prime. If there was two, you'd say double prime or triple prime or those type of things. So, and then the dy dx is basically representing the d stands for the change of. So it's the change in y over the change in x, which is exactly what your slope is. It's how fast your time or distance is over time, things like that. It's how fast things are changing. Okay. The reason we don't use when you are looking at change, you'll see the delta. So the difference between those is the delta represents change over a specific length, where the d represents that limit as that change is going to nothing. So that's where that difference is. So the delta y over delta x is the change that we typically see, and then the dy dx is the calculus of it as that limit's going to zero. All right. Notice nothing is going to change from what I did, except for now they say we're going to find the derivative of this function. And we're going to do it backwards. We're going to actually do a first, and then we're going to find 2. So f prime of x is the limit as h goes to 0 of what's f of a plus h. So I've got remember, we're going to change all these to a plus h, right? All right, so a plus h squared minus 8a plus h plus 9 minus a squared minus 8a plus 9 all over h. Okay, clean up the top. The algebra correctly. That's the right answer. You can get rid of the brackets. It's more just making sure you do your signs correctly when you're. Oh, okay. You ever see the extra part? The -6 squared -6 that. This one after the. Right. Oh, yeah, yeah. Which is gonna help clean some stuff up in a second. I know, it's a lot of little things. So what you should end up getting down to, after all the cleaning up on the top, you should end up having H, sorry, 2A minus 8 over H. Right? Or was there an extra H on top? What was it on top? Because I didn't know because we're doing it. Oh, it's just plus H? Okay. Yeah. Okay. So that is being just 2A minus 8 plus, and then the H goes to 0. So that ends up being your answer. And next Tuesday, I'm going to show you how to go directly from here to here without doing any work. One of the very first rules we learn in derivatives is that one. But you can start to see how, like, the problem is that one semester I actually said, you know what, it's stupid to spend all this time going through and doing it. And then I ended up having after like halfway through the derivatives, having to go back and show them this because they had no idea what the heck it was. So I'm like, all right, I'll take the class and actually explain the concept behind it, even though you're never going to actually do it out. Because it isn't important to understand that the derivative is the slope and how it instantaneously changes and whatnot and why it's useful to do before we actually go in and give you the rules that basically eliminate all this work. All right, so we've got that. And if we plugged in 2 to that, we would get, so the f prime of 2, because that's 2, would be 2 times 2 minus 8, which is -4. Yeah. So yeah, you did with that, or you did yours with X. Right. Yes. Yeah. Yeah. Actually, those probably should have been A's, but we didn't go to A. So it should just be F prime with A. Yeah. Yeah. Again, the wonderful little thing, we're never going to use A's after this week. All right. Find me the derivative of this. And if you won't, just because the A's can become a little more complicated, you can use this. Just leave it with the X, which is fine. Oh yeah, that is a 0, not an 8. Ignore the one hint I will give you to make your life a little bit easier. Ignore the H on the bottom right. All the work's on the top. Okay. So sometimes if you're writing, especially when you're going to have fractions over fractions, things like that, like write the top first and just see if you can clean up anything at the top before you have to deal with these. Okay. Sometimes you won't. Sometimes you're going to have to use the H right away and have to do some work with it. It's fine. But work with the top first, get that set up and work right, and then indicate something. Here's this problem. And don't change it to bracket. Don't change it to that book. Keep the square root. Yeah. Okay, because no, this is fine. That goes over the whole thing. You got her set up right. That's good. Now, sit back to, you got it set up right. So the next question after you get it set up correctly is, how do you get rid of the square root? That makes a really big difference when you're doing your work next out. Perfect. That's exactly what you have to do. Yeah, well, which is fine. No, it's fine. It's just not going to help. Because if you're going to go H to 0, that's still going to 0. This would work great if we were going to infinity. But since we're going to 0, those are still going to be 0 on the bottom, and you're still going to be 7. Yes, that's exactly. Oh, you're fine. Oh, as H goes to 0, this goes to. Yeah, so you did it, but you didn't get rid of the other H. A couple of things I saw when I was going around. The first thing is, so sometimes the way you're writing things can screw you up. So f of x plus h is the square root of x plus h. The square root goes all the way over the h. Okay. The reason that's extremely important in this case is because otherwise you're going to see square root of x minus the square root of x and going to cancel them out when you can't, because they're not actually the same. Okay. So just keep that in mind. Because this is replacing the x. So we're not adding h to outside the function. So it's not f of x plus h. That would be the square root of x plus h. It's inside the parentheses, so it's replacing that x. All right, so in this case, there's nothing I can do on the top to simplify it down. So what was the method that we had done previously when we had square roots? Yeah, conjugate pairs. So if I multiply in this case, the top by the square root of x plus 4 plus square root of x over the square root of x plus 4 or plus h plus the square root of x. Now, on the top, we have x plus h minus x. And on the bottom, we have h x plus h plus square root of x. So these x's cancel out, and I'm left with just the h on the top. And the h's now cancel out. So I have 1 over square root of x plus h plus square root of x. I still haven't done the limit, though. And the only reason I made sure I write that in there is because I saw a couple of people actually not do this part. There should be no h's left in your problem when you're done. Okay? So as h goes to 0, this becomes a square root of x, that becomes just a square root of x. So I have 1 over 2 square root of x. All right. So that's the square root of x, right? What's the domain of the square root of x? It's 0 to infinity, including 0. Right? I can do the square root of 0. So it's including 0 to infinity. All right. So as this is getting up here, this right here, that slope's getting very, very close to what? No, the equation is getting really close to 0. What's happening to the tangent as we get closer and goes this way? Is it getting bigger or smaller? Getting bigger, right? If we're going this direction here. So basically, this is almost a straight line up and down, right? And as in terms of slope, that would basically be an infinite slope, right? That'd be a vertical line. Let's look at my. Now this was my derivative. So if you notice the derivative, what were we saying? This is getting bigger and bigger, right? And my derivative is getting bigger and bigger. So my slope's basically going to infinity. And as this keeps going out, it's starting to get a slower and slower slope, right? And as you look here, it's getting closer and closer to what? Getting closer and closer to 0. But it'll never quite reach there. Okay? Because this continues to increase. This increases slower and slower and slower. Never quite reaches the 0. Okay? All right, let's look at a different equation that's a little bit easier to understand and not these. All right. So here's my equation, x to the third minus x. Cubic function, right? Okay. What are some of the key points on this graph? When you were back in pre-calculus, what were some of the points that you had to graph? Huh? The maximums and minimums? Okay, so right there and right there. Those are my maximums and minimums. Oh, that's kind of cool. You can now click on it, and that's nice. That's kind of helpful for other things. All right. What are some other points that were kind of important to know? Okay, the zeros. Got zeros there, 0 there, and then the end behavior, right? In this case, my x-intercept and my y-intercept are both 0 in that case. All right. All right. This, the black line, is my derivative. What are some relationships between these two that you notice?
At the minimum and maximum, the derivative is 0.
Very good. So right here, those are the same points, right? Why? It's changing direction. So my slope, that's going to have to be 0, right? Because as it's going to getting closer and closer to its maximum or minimum, it's got to slow down, right? And then it turns. So at that point, my derivative is going to be 0 because that would be a horizontal tangent. What do you notice happening between the two, the min and the max? On the original function, what's happening between the min and the max? Which direction is the function going? It's going down or going up? Sorry, from the max to the min, technically, in this case. So right here, so if we ignore those, from here to here, which direction's the function going? It's going down, right? So my slope would be what? Slope would be negative. Let's look at my slope equation. Notice between here and here, my slope is negative. Okay, so the derivative is helping me, is actually going to give you a way to be able to graph a function even easier. If you know where the functions, when the derivative is negative, you say, okay, now I know my function's going down at this point. Okay. And then before that point, so before the max, this is going positive, correct? It's going up. And my derivative is on the positive section. Same concept over here. After the minimum, it's going up. And after that point, my derivative is positive. Okay. What's the red line? Okay. So what do you think this line tells you about the graph? It's telling you the slope of the slope. So if we ignore this one, we can look at the same concept, right? So at this point right here, my derivative is 0, correct? That's my minimum, right? And that point right there is where it crosses the x-axis. Okay. So what the second derivative actually tells you is concavity, which I'm not sure if you talk about pre-calculus or not. So something we're going to talk about. If you notice, it actually splits the graph in half, basically. It's telling you this part right here is concave down. It's looking down. This one's concave up. It's going up. We will talk about it a lot more later on, not right now, though. All right. So let's look at this equation. All right. What do you think the derivative of this function is going to look like? So remember, derivative is telling you slope, correct? Okay. So what is the slope of this equation? Well, where is it 1? I know. Oh, hold on, I got to do it greater than 0. That's right. So that side's 1, right? And the other side is -1. So what's the derivative right there? Doesn't exist. Remember we were looking at limits when we were looking at the limit of this one originally? The limit at that point in the middle didn't exist. Because for a limit to exist, it's got to go to the same point. It's got to go to the same place, right? From both directions. In this case, it doesn't. So in this type of situation, we have a problem. We can see where we have a situation where a derivative might not actually exist. Okay. So the absolute value of x is differentiable only on either direction. So it is differentiable when you can take the derivative of it. So it's kind of like, does the limit exist or not? That's the concept. So can I take the derivative of it? Since the derivative is a limit, okay, since it's going to a specific point, if I can't do the limit of it, I can't take the derivative of it. So in this case, it's differentiable from -infinity to 0 and 0 to infinity, but not including 0. Okay, I cannot find the derivative at 0 because it doesn't exist. So there's a few situations where a function cannot be, or the derivative cannot be found. Okay. One is the corner. Okay, so that's like we just did with the absolute value. So if it goes to a point, that derivative does not exist because the limit doesn't exist at that. Because remember, we're looking at the limit being a slope in this case. So if you're looking at going to that point, the slope's getting infinitely large on this side. And on this side, it's a positive slope. On this side, it's a negative slope. And it changes instantly. It's not a smooth transition. So in that case, since it's going from positive to negative, it cannot exist. We can't have a situation where there's a discontinuity. Okay. So because again, the slope going this direction, the slope going this direction is going to be two different values. So therefore, it doesn't exist again. This one's a little tougher. It's when you have a vertical tangent. They didn't do a very good job of a vertical tangent because this vertical tangent actually is continuous. Normally, when you see a vertical tangent, it looks like this. But they didn't want it. They wanted to differentiate it from a discontinuity, where this would be a vertical tangent as well. So you can't have a vertical tangent because in that case, the slope actually goes to infinity. And we can't have a derivative be infinite. All right. So remember we talked about continuity before? Did I just copy it? I did. Hold on. So this is the one theorem that's actually important. If the function is differentiable, which means I can find the derivative of it, then it is continuous. at any of the values in the domain. So if the function is differentiable, then it is continuous. And since it says that since A can technically be anything, it's the same concept. It's, as long as it's differentiable over the domain, then it is continuous over that domain. So the question then comes, is the converse true? Do you remember what converses are and not the sneaker? Huh? Right. So converse is flipping. So if f is continuous at A, that means it's differentiable at A. So that question is that true or not? And no, we just showed one, right? When we looked at this situation here, is the absolute value continuous? Does that have an answer at 0? Because there's no holes, right? There's no asymptotes, right? There's no discontinuities. It is continuous, but it's not differentiable. So the converse of this statement is not true. So if f is differentiable, then it's continuous is true. If it's continuous, then it's differentiable is not. So you can't go the opposite direction. So even though if you know a function is continuous, that doesn't necessarily mean it is differentiable at everything. Okay? And actually, technically, this situation right here, that is continuous. There's no gaps in it, but it is not differentiable. This is the only situation actually out of these three that is not continuous. The other two are continuous. It's just not differentiable. All right. Well, since I already did that problem, I'm not going to use that equation. So let's do a different one. Um, hmm. Let's use this one. Actually, I don't like you that much. I don't want to use that one. We're going to use a harder one. All right, find my derivative. What did I tell you? Do it piece by piece. Don't try to do it all at once. So if I were you, the very first thing you would do, you should look at is, remember, it's just basically we're changing it to u plus h, right? So then I have u plus h plus 1 over 4 u plus h minus 1, right? Do it in pieces. And you can clean that up a little bit if you want. So then I have u plus h plus 1 over 4u plus 4h minus 1 minus u plus 1 over 4u minus 1. Okay. The biggest pet peeve of me when I was teaching high school algebra is because in elementary school, they taught this and they told the kids, just cross multiply. Not cross multiply. You can't cross multiply without an equal sign. And it was like, we're trying to solve one with the equal sign. It's like, that's not cross. It's like, you multiply the denominators by the numerator. It is a cross, yeah, but it's not cross multiply. Oh, yes. I did say I didn't like you guys to write the problem. I really wanted to see if you guys could actually work. Okay, you made a mistake somewhere. Because if you can't get rid of the H, something's wrong. You should always be able to get rid of the H. If you can't get rid of the H on the bottom, it's something got a mistake on the top. Okay, I was gonna say, yeah, that doesn't go back. So did I miss a sign here? Hold on. Oh, okay. All right, so that cancels out with that. That cancels out with that. And I'm left with negative 6u plus minus 5h. And that cancels out. And that cancels out with that. Did I screw up the sign somewhere? Four u squared minus u plus 4hu minus h plus 4u minus 1. Okay. 4u squared, 4hu minus u, 4u, 4h minus 1. Yes.
Hey, getting that one over.
This? That was, remember, it's, the function was the limit as h goes to 0 of, in this case, it's g of u plus h minus g of u over h. Did anybody get to that point and tell me where I'm missing? Like, did you get something different than me? That's what you should have. And I'm trying to figure out where the heck I screwed this up. Right. So they should either be this. Oh, right here. That's plus 4u. There's the mistake. Okay. I'm like, that shouldn't be there. Like, those should have canceled out. I was trying to figure out why. There's the mistake. Okay. So let's cross out. All right. So if you notice, even doing it my way with splitting it up, still really easy to make a mistake on a sign. But that's, remember what I said. The goal is you should only have an H left. If you have other stuff left, you probably made a mistake somewhere. So that's why I'm like, I knew the 6u was going to screw me up. It had to be gone. So I was trying to find that mistake. But notice how I have not even touched the bottom part. That's literally just dealing with the numerator. Okay. I want to clean that up as much as possible before I start making it more complicated. All right. When you're going through and doing these problems, even when we start looking at derivatives and stuff like that, you want to figure out ways to simplify down your work as much as possible as you're going. Okay. Because these problems can be very complicated going forward, especially like later on in Calc 1 and Calc 2 and things like that. They can become very complicated unless you like work in pieces. Okay, so I did that one side, I did the other side, then I subtracted them, and now basically the whole top is just that. So now I have this. I have negative 5h over 4u plus 4h minus 1 times 4u minus 1. All over h. Because remember, I took that minus that all over h. So all this work here was just the numerator. Because this would basically be whatever the top is times 4u plus 4h minus 1 over 4 minus 1. So this whole part right here, this whole piece right here, is that. Huh? Yeah. So now I do my, notice I did not multiply the bottom because I don't need to, times 1 over h. So the h is now cancelled out. So I have the limit as h goes to 0 of negative 5 over 4u plus 4h minus 1, 4u minus 1. 4u minus 1 squared. Okay. Yes, lots of steps, lots of little places to make mistakes, as you saw I did. Yes. This way. Mistakes happen. The biggest thing when you make a mistake is realizing you've made the mistake and how to go back and find it. It is actually one of the big reasons I don't pre-prepare all my slides. Like I actually do the problems live on purpose because if I make a mistake, I then actually show you basically how to find it, which is helpful. So you have to realize where you made that there is a mistake and how to fix it. That's actually just as important as getting the right answer. All right. So that's the derivative of this function. I would love, well, it's slightly easier. The quotient derivative actually is probably the hardest one to do, even like actually as a derivative. It's not as complicated as this, but it is not necessarily the simplest one to do. All right. Let's look at some word problems. You ever watch the show Gold Rush? They're trying to actually get gold out of the ground. All right. So the cost of producing X ounces of gold from a new gold mine is C equals F of X dollars. All right. So this could be anything. Like the cost of producing X number of toys is this dollars. So whenever you're looking to produce something, your cost of production is a certain amount, right? Typically, your cost is what? Think back to when you're looking at how would you figure out the cost of producing something? What are the two things that would go into it? Cost of material. And would that change based on how many I'm making or stay the same always? Right, but if I'm going to build a house, we'll take a house. Look, I'm going to build a house. The cost of materials to build one house, we're going to build a complex with all the exact same houses. The cost of materials to buy a house is dependent on how many number of houses I've built, right? So that's going to change. So the same thing here. The cost of producing X ounces of gold or X number of items, that changes. So the cost of materials would change. What would stay? That there's another part of the costs. That's your fixed cost. That would be like if you're building houses, that'd be like your tools, right? Those don't change. You're going to buy those once and you're going to have them. Until they break down, you have to buy more. But for the most part, those are going to stay the same. So your cost is your fixed costs plus the cost of the items, right? And that's going to change. Think about this for a second. What's that look like? Okay, it's a linear equation. They can get really complicated equations, but it breaks down to basically a linear equation. All right, what's the meaning of the derivative? Okay, and in terms of this, what's its units? Dollars. Slope's got to be something, right? Dollars per ounce. Yeah, I know that's fine. And this problem, it's dollars per ounce, dollars per house, dollars per toy, whatever it happens to be. But it's dollars per. Remember, slope's got to be a division, so it's got to be something per something. So it's dollars is on top because that's your y over ounces, which is your x. Okay. So what does the statement f prime of 800 equals 17 mean?
Dollars make 17 ounces.
What's the x? Go forget the houses. Go back to this, like the actual this one. So we keep the units the same. 800 is the x, which is your ounces, right? X is your ounces. That's x. So what's the 17 represent? It's dollars per ounce, right? Okay, so for 800 ounces of gold, at that exact point, it's costing me $17 per ounce to produce. Okay? Does that make sense? So if I want to produce 800 ounces of gold, it's going to cost me $17 per ounce to produce, which would be a hell of a deal considering gold right now is about $2,500 an ounce. So if I was to produce 900 ounces of gold, would it still be $17 an ounce? No. Would it be more or would it be less? Why?
Because there's a greater quantity.
Okay. And what's going to increase? The only thing that's increasing is the material cost, right? That's the only thing that's going to change. So the fixed cost is going to stay the same. And as you're going over more, that gets itemized over a bigger thing. So it's going to go down. So your derivative will typically, in this case, would decrease over time. Okay. Good. Let's do. Yeah.
If it's a linear, shouldn't the bar with it?
I was using this as a very simplistic explanation. Normally it's it's a lot more complicated. Actually, in that case, you're right. If it was a specifically linear, the slope would be the same at all points. So in that case, it would always be 17.
If we don't.
So in this case, it was just that. Honestly, there wasn't an actual one specific answer for this. It was, what do you think would happen? Typically, what ends up happening in most businesses is the longer you make it, basically the cost per item decreases. So therefore, your slope actually decreases because your fixed cost is itemized over a larger amount of the actual costs. So it's a lot more complicated of an equation.
If you-
Yeah.
Even though the actions.
Right. Exactly. Go buy 400 eggs, you're going to pay less per egg than if you buy six eggs. Okay. Although now nobody can afford 400 eggs. So, all right. Like H of T equal the daily cost to heat an office building when the outside temperature is T degrees in Fahrenheit. What is the meaning of H prime of it, or H prime of T, or H prime of 58? What's the meaning of the derivative at that point? All right, we'll take the other question. What are the units at that point? Cost per degree. So it's telling you how much you're going to pay for heating for every degree it changes. Every degree it goes up or goes down. So would you expect it to be positive or negative? H is what? Heat, right? So would you expect the temperature to the derivative of it to increase or decrease as the temperature increases? It would decrease because we're not going to have to pay as much for heat. So in this case, it would be negative. The colder it is, the more heat you're going to use, the more it's going to cost you. The warmer it is, the less heat you're going to use, the less it's going to cost you. So it's negative. Okay. All right. I'll do one more. Okay. One's the position of the car, one's the velocity of the car, and one's the acceleration of the car. Which one's which?
At some point, I might slow down.
Okay, so if A is the accelerate, so let's think about. So remember, we have position, velocity is the basically p prime, right? Or actually it's s technically. So that's s prime. And then acceleration, which is the second derivative or the derivative of the velocity. So what did we know about the graphs? What was the key piece of information when we were looking at that first graph? We're looking at the derivative of it. We're looking at the what? And when did it change? The slope was positive or negative, but when did it change in the actual graph? Not at the zeros.
Oh, I think that.
The maximums and the minimums. Those are the key pieces, right? The maximums and minimums is when it changed. Okay. So if we look at A, where's the peak? Right there, right? And that's the min, right? So if A was, we were taking the derivative of A, one of these has to be 0 at that point, correct? Yes? And it's not. Okay. So A is definitely not the position. What about this equation right here? To that point, it's what? So up until that point, the derivative is going to be positive. And then after that point, from here to there, the derivative is going to be negative, right? Which of the two equations kind of matches that? So A has to be the derivative of B, right? Because up to that point, that's basically right there, right? I might have been a little off of my line, but there. Okay, so we have B of x. The derivative of B of x is A of x. Okay.
I was gonna start to do that.
All right, so let's look at that. Change this so I don't erase this on me. So now let's look at C. C is always positive, right? Okay. Well, B is always positive, so that's. But it seems to go fast and then start slowing down, right? Is that what C is doing? Seems to be going fast and then all of a sudden it starts slowing down to go to 0, right? All right, so that means that B of x is the derivative of C of x. So then that would be the position. So C would be position. B would be accelerate or velocity. And A would be acceleration. So you can start to look at how the graphs move to determine which order they go in. A velocity? Because so it's positive here, right? So this is positive. That's not what I wanted.
I didn't even have the first base, so I know that.
So acceleration, so velocity is easy. We always talk about velocity. That's speed, right? We talk about in the car. So acceleration is how fast is your speed changing? That's what acceleration is. So when you push down on the accelerator in your car, what happens? Your speed increases, which increases how fast which increases your distance you're traveling, so your position's changing faster. So it's how fast does your speed increase? So it's actually it's distance squared over time is in essence how it ends up being, because it's the change in velocity is that over time. Or no, sorry, distance over time squared. So if you're thinking about like when you let off the accelerator, you're no longer accelerating, so it's now a negative speed. So because you're slowing down, so your acceleration's negative. So, and you can change that by hitting the brake and stuff like that to actually slow down faster, but that's all basically what your acceleration is. That's why your acceleration is typically a lot more chaotic than the other two. All right. You're done. Remember, no class Thursday. Don't come